Alright, welcome back Physics 30. What we're going to learn today is continuation from our lesson number 1. Lesson number 1 was talking about how in the world of physics we are start to bring the concept of particle for as a start light. And in the end, it is still debatable that what is matter. And when I talk about matter, subatomic particle like electron, proton, neutron, are they particle or wave? There are still a debate. But long story short, we were focusing on light. And yesterday, we started going into wave-particle duality, which is light generally behave as wave, but there are some occasions where it behaved like particles. And today's lesson is photoelectric effect, and this is one of the main key discovery that light may behave as particle, and it's discovered by scientist Hertz. You heard about this Hertz before because we use it as a unit for frequency. Now, the workbook page 39 is where I am, and we are going to go through each situation. And when it comes to this lesson, I kind of divide this into half. It's not 50-50 half. One of the lesson is about 75, which is this recording part, and another part will be about 25 with multiple different graph analysis. Graph play a huge role in diploma. So here's the thing. Whenever there's a high frequency of EMR, we learn that high frequency of EMR can have high energy because E is equal to HF. And if high frequency EMR is shown upon any type of metal, and when it comes to this, it's a cathode ray tube. It's a famous experiment that this is not a cathode ray tube, but you can kind of see a similar situation, cathode on one side, anode on another side. But if it's happened to go through one of the metal electrode, there scientists detect that electrons are generated, and it was one of the most incredible phenomena, because that means photon energy is somehow converting into electrical energy, which is what we see in solar panel too. And explaining this concept is quite tough, actually. It's a university level. But in any case, I'm going to go through Physics 30 level of explanation. And whatever this electron that is emitted due to the bombardment of EMR, we call this photoelectrons. And they travel to, of course, opposite electrode known as anode. So when it comes to this electrode, cathode is the one that have a bunch of continuation of photon. As you may notice, I am putting a shell around the wave on purpose, because this is basically what wave-particle duality explains. Light can become a particle, and the reason this is particle is because particle bombard momentum can give kinetic energy. Think about it that way. So cathode is the one that is being bombarded, and after that electron will go to anode, and we discover our current using ammeter. And if you guys remember, current is how much number of charge over certain time, and you use amp, of course. This diagram that you see over on the right side is known as photocell, because if I cut this into two half, photo, like the word says, light, cell is a basic unit of battery, so you can think of light battery. It is a unique source of electrical energy, and this is one of the most useful green energy technology that we humanities are studying, basically. humanity is studying, basically. We cannot burn fossil fuel all the time. Now, when it comes to this photoelectric effect, there are two different types of explanation. There's classical and there's modern, which I call actual result. Now, this is where old hypotheses and theories collide with modern theories. Classical prediction was simply this: E is equal to HF. So, if you think about our first lesson, whatever the most brightest means whatever that have high intensity will basically emit more number of photon, and because it has more incident EMR, more and faster energy will be delivered to the cathode, from cathode to anode, something like that. This is classical prediction. So what they were predicting basically was what you see at the bottom. Now, it was, I think this is a way that you can see everything. So whatever intensity and whatever the energy that we got, or in this case current, I guess, they predicted like this: zero intensity to high intensity. Now, long story short, this is not true actually. This hypothesis was not supported. And this is where things are getting quite tricky. Long story short, I'm going to go through what was discovered first. Originally, when it comes to zero intensity to all the way higher up, so imagine we start with low frequency, so that's like radio wave, all the way to gamma situation. The funny thing is, intensity didn't matter. Whether it's dim light, bright light, it doesn't play a huge role when it comes to actual electron that is generated by bombarding EMR. Because from low level to certain level, we had nothing. No electron was generated. But after a certain point, we start to receive a certain amount of current. And we found that there is suddenly a big jump over there. And of course, scientists had no idea at the beginning. And that's physicists' job to understand this phenomena and evaluate that, analyze data, and conclude what was a discovery. So, what we found, first of all, this jumping point frequency as fundamental frequency or threshold frequency. Anything that below this frequency does not generate any type of current. This is very similar as if you took any of a biology theory courses. It's like how neuron works. There is a threshold millivolt of stimulus that has to go through the neuron to activate the nervous system. If it's below, it doesn't react, something like that. And one of the conclusions that they made was, if the incident frequency is below this threshold frequency, then no electron, regardless of how bright you set the machine up. So for example, if this is my visible light frequency, anything that below here, so that's microwave, radio wave, infrared, those basically do not generate any type of electricity, even if you set it as the most intense level. So the amount was not the part of the question when it comes to intensity of the light. But if you go right after, so UV light, X-ray, or gamma ray, anything like that, even if you set it as very, very, very dim way, as long as photon can go through and bombard the cathode, physicists detected that there is electron. Of course, at this point, so when I'm talking about this area, then we can apply some classical physics explanation. Then we can control how dim, how bright, and at this time, maybe you can get more electrons, something like that. So any frequency that is above the threshold frequency, at this part, electrons are immediately emitted, and no matter how dim it was. Of course, if you want to go intensity and current situation over here, you need to understand that there is a condition. My frequency have to be higher than the fundamental or threshold frequency, and every metal have different frequency, and that will now correlate to our classical bright light. Probably will have higher intensity, so you will have higher number of electron, and dim light will have low, something like that. So let's do theory question over here. If the threshold frequency for a certain metal is blue light, then describe the nature of the photocurrent as answer no current, low current, high current, if the incident light is number 1, dim violet, number 2, bright orange. So let's think about our visible spectrum. We have, let's say this is low wavelength, high wavelength. You know what, that will make my life a little horrible because that means red is here. You know what, it really doesn't matter. Red, so low frequency, high frequency, red, yellow, red, orange, yellow, blah, 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 all the way to violet. And blue is kind of located over here. Indigo and then, yeah. But in any case, it's not exactly in the middle. Middle is generally green color. Now here's the thing. Let's go with A first, violet. Now you may notice that this point is my fundamental frequency. So anything that bigger, which is on the left side over this question, works. You will have electricity. So you will know that, yes, there will be current. But since it's dim, that means you will have low current for this certain metal cathode or metal photocell in this situation. So that's my answer for the first one. And this dim and bright will play a huge role for that situation. What about the orange? Well, if you look at the orange situation, orange is basically lower frequency than the threshold. So because it's lower than F0, you need to understand that there is zero current, no current. Now, at this part, brightness, so intensity, doesn't matter. The way that you will play bright or dim color and how those two interact a lot for the current, there is a basic condition. Whatever frequency should be higher than threshold frequency. And this doesn't fit to that first category. So bright and dim is out of the picture. Whatever the orange color, no current at all. What about if you have, for example, bright indigo? Something like that. Then this one, yes, you will have a current because as I mentioned, indigo and violet color is actually higher frequency than blue color. If you think about the rainbow, it will make sense. Now, bright part also now play a huge role too as soon as you see the bigger than F0 condition, because bright means higher intensity, so you will have high current situation. Now, about low and high, we need to do some calculation. And that leads us to the next page. So, first thing first, we gotta explain why we have this sudden jump after the fundamental frequency. Why not does it like gradually increase like the classical theory. It's because, and this is Einstein explanation, which is verified wave particle duality of EMR, light in this situation. He commented in this way. Basically, any type of metal, and I'm going to draw Bohr's model over here. You have proton, neutron, and if you're really into physics, you may notice that Bohr, Einstein, they are not much of a good friend when it comes to scientific discussion. So here's the thing. Although I draw only one electron, actually, you know what? Let's draw two, like boron. Boron has 3 electrons. So you have 2 electrical energy level. So Einstein explanation was this. If I have a lot of bombardment of EMR, so E is HF, so a bunch of energy that you get, then here's the thing. This will eventually make electron go away from that metal. Of course, this boron example is boron is not technically metal, but you got the idea. You can think about copper or something like that. But here's the thing. There must be some kind of energy to make whatever the electron that is located at the most outer side, which we learned it as valence electron in chemistry 20, and some kind of energy is used up to dig this electron and shoot it to the opposite side. Then where does that energy come from? And this is basically what Einstein supported. Incident EMR that have higher frequency than fundamental or threshold frequency has enormous energy to basically dig the electron out of the metal, and we call this energy work function. That's like basic minimum energy to shoot electron from one end to another end. And this work for ionization. Like, for example, how you can make copper into copper 2 positives. Something like that. Only one photon, according to explanation, can be absorbed by an electron in a metal surface. So, if you remember N and E that make a ET, total electron, that is emitted by each of the photon, that calculation still work in here. E photon is equal to HF. We know this formula from previous lesson. And by controlling this as an incoming energy and the kinetic energies that follow by, we have 2 explanations. If my frequency is smaller than threshold frequency, then here's the thing. My photon energy, which is E is equal to HF, is too small to shoot the electron from cathode to anode. It is basically smaller than work function, which means cannot even dig electron out of it from this shell. So, because of this lack of energy, removing electron is impossible, so no current. However, if F is exactly equal to my fundamental frequency, then what's going to happen is just enough energy to remove. So whatever the number bigger than that will be now go to electrical energy. If it's F and F0, you technically have no electrical energy at this point too, which lead to our number 3. What if frequency is bigger than fundamental frequency? Well, then it actually worked because whatever incoming HF I'm going to put, having enough of energy for work function and whatever kinetic energy for my electron. So we have excess energy. And how that excess energy will be used is, well, now sending the electron to anode situation in the photocell. That's basically the situation. So let's do some calculation of these 2 situations. And by the way, before we getting into this, number 3 is kind of repeated over here. If the frequency is bigger than F0, photon energy is greater than work function, then that means we can dig the electron out of the metal. That part is done, and that's W. And second part is the rest of the photon energy will have kinetic energy that make electron move from one place to another. So conservation of energy perspective, I can say my total energy initially should be equal to my final total energy. Conservation of energy, of course, which correlate to my dot point over here. On the right side, I have W plus EK, and you guys know the formula for this one. EK max is basically, you can consider W is HF0 plus 1 over 2 m, I'm going to put electron because it's mass of electron that we're, motion of electron we're discovering, and 1 over 2 mv squared. Now, here's another thing. If I think mathematical relationship between frequency and wavelength, can you just put lambda maximum, because these two means the same thing. If I have minimum frequency, if I think everything as a flip-flop way, that means wavelength is maximum. So minimum and maximum, something like that. If there's a minimum wavelength, then that means it's a maximum frequency, but we don't do maximum frequency. We only talk about minimum frequency, which is threshold frequency. So have that in your mind. So if I have greater frequency amount, that means I will have greater kinetic energy because I have more extra energy. That's something that you may want to know. Let's do two last example. Number 2, the minimum energy to emit an electron. So we are talking about minimum energy. That means work function. To emit an electron from a metal is 3.55 electrovolt. Determine the maximum wavelength of it. So, like I mentioned, work function is HF0, and that's fundamental frequency. Now, if you think it as a flip-flop situation, minimum frequency means it's a maximum wavelength. So I can use this W and HC lambda over here. And if I modify this formula in terms of wavelength perspective, it's HC over W. And maximum frequency is, now you can use other form of W, if you will. Oh, sorry, H, if you will, instead of joule. 4.14 10 to the power of negative 15 eV and S. 3 10 to the power of 8 meter per second. And W, my work function, 3.55 eV. So that eV cancel, second cancel. I have my lambda. Then you have about 3.50 10 to the power of negative 7. If I want to change into nanometer, just multiply 10 to the power of 9, which will give me about 350 nanometer, which I believe is slightly below visible spectrum. So it must be like UV to violet, somewhere over there. That is my answer for example number 2. Now my last example. So we did one theory example. Second example was minimum, so work function. So we went to a threshold frequency and maximum wavelength. Now this is the part where frequency is bigger than fundamental frequency. So let's talk about that. The work function for a metal is 7.20 electrovolts. So this is minimum amount to dig up the electron from the most outer layer of atom of metal. You can think it in that way. Valence electron. If 4.00 10 to the 15 hertz EMR is shown on the metal, determine the maximum speed of photoelectrons. So As soon as you see this, of course in real life or diploma, it is good idea to double check whether this energy exceed the W or not. But right now we are talking about the speed of photoelectrons, so I'm assuming that this is already bigger than fundamental frequency. So here's what you need to put. Initial energy, I like to say incoming energy, which is what I'm going to use for this one. That is equivalent of W if these two are minimum plus EK. E incoming is HF. That is basically what I have over this side. Work function we know as 7.20 plus 1 over 2 mv squared. But here's the thing. If you think about kinetic energy, it is joule, right? So that means it is good idea to convert this electrovolt into joule too. And we're going to do that as a little pre-step. But let's do that first. Let's do these two calculations first. So what I mean by that is 1 over 2 mv squared is equal to hf minus w. Let's do this portion first, which means I'm going to do use joule. Like I said, kinetic energy use joule. That's why. That's the only reason. Oops. Oh yeah, it is correct. I just use simple ratio to figure out the conversion of 7.20 into 7.20 is equivalent to joule. And the difference between them provide you about 1.50 10 to the power of negative 18 joule, and that is 1 over 2 mv squared. And of course, if you want to be detailed, m is mass of electron. So now, to find out the maximum speed of it, 1.50 10 to the power of negative 18 joule times by 2 divided by mass, 9.11 10 to the power of negative 31 kilogram, and square root. And that provides you 1.81 10 to the power of 6 meter per second as a maximum speed. And that is the lesson for today. Your to-do list is basically page 41 and 42, but please do 5 questions, 1, 2, 3, 4, 5. Don't do section B yet.